In this lecture, I'm going to cover the materials that are presented in chapter 1 of our textbook, which you can view online. You can also access the source code for the textbook in case you want to rerun the code yourself. And if you want to buy a physical copy of the book, you can get that too. So what I'm going to do is I'm going to walk you through some of the leading ideas in chapter 1 of the textbook, but I do expect that you will go back and read chapter 1, the textbook itself. It's not enough to just listen to this lecture to understand the details, because I'll be skipping some of the topics that are in chapter 1. So before I start, I want to just quickly motivate why we are going to spend so much time. Well, it's not going to be a lot of time, but we're going to spend a little bit of time on understanding these foundational ideas that are needed for statistics. So the basic issue is that whenever we collect any kind of data, we are assuming that the data are coming from a particular random variable. That's an assumption that we make. And in order to understand what we are assuming, we have to understand the concept of a random variable. And that's what I'm going to spend a few minutes on. I want you to understand what a random variable is, what its properties are, and what you can do with it. And in particular, I want you to understand the important concept of a probability mass function or a probability density function in the random variable, because this plays a crucial role in all the statistical modeling that we'll be doing in this book. So one important thing to notice is that the ideas that I'm going to present here are usually not taught in introductory statistics classes, in linguistics and in psychology. Some programs might do that, but the programs that I encountered as a student myself did not teach these ideas. And I think that is a very big mistake. The alternative approach that people often take, which is this cookbook approach to data analysis, this leads to all kinds of misunderstandings and misinterpretations of the statistical models that we use for data analysis. So I would strongly encourage you to spend maybe one day trying to understand how this machinery works, the random variable, and you will find that once you understand these basic ideas, your ability to do statistical modeling will become much more effective, and you'll be able to draw correct inferences from the data that you're analyzing. So let's move on to talking about the first important topic, which is discrete random variables. So I'm going to introduce the concept of random variables by talking about a very simple version of random variables, discrete random variables. And so at the highest level, at the most abstract level, a random variable is a function that goes from one set, which I'm calling big omega here, to the set of real numbers. So what this function does is that it associates every element in the set big omega, which we are going to call an outcome from an experiment. It associates every outcome with a number, right? So formally we would write it like this here: capital X, which represents the random variable I'm talking about. Small omega is an element of the set big omega, and X is a real number that the random variable maps that outcome onto. Now the set of all the elements X, and this could be finite or non-finite, these are called the support of X. So which I will refer to the support of X as S of X. The support of X will informally speaking, what the support of X represents the set of all possible events that can happen in a particular experiment. And I'm going to make that concrete in a second. Okay? And so the support of X is very important for us to understand in order to unpack the nature of the generative process that we are assuming when we are trying to analyze data. We are always assuming that the data are coming from some particular random variable. So let's take a concrete example. So suppose we are tossing a coin, and the experiment is the following. I'm going to keep tossing the coin again and again until I get a heads. I'm going to stop when I get a heads. So what can possibly happen? What could happen is I toss the coin once, I get a heads right away, right? So that's one possible outcome that I could have. Another possible outcome could be first I get a tails, then a heads, and so on, right? So this could be an infinite set of possibilities out there. So in this situation, what's happening is that the random variable x is mapping each one of these outcomes, a heads or tails followed by a heads or two tails followed by a heads, to a number, right? So that's the function that you're seeing being unpacked here, right? I've just given 3 examples here, but you can see what would happen now. That in principle, this the support of x is going to go from 1 all the way up to infinity, right? So that's the support of x here in this particular example. Another example that is even simpler is the example of tossing a coin just once, right? And checking whether you get a heads or a tails, right? So if we think of this particular experiment, there are only 2 possible outcomes that can happen, heads or tails. And what the random variable does is it maps each of these possible outcomes to a number. We have just made an arbitrary decision to map tails to 0 and heads to 1. I could have done it the other way around, right? So, or I could have chosen some other numbers too, you know. So it's not set in stone that I have to use 0 and 1, but it makes sense here to talk about failures and successes if success means getting a heads. So one very important idea in random variables is the idea of the concept of a probability mass function. That's the discrete random variable case, and a probability density function, which I will talk about in a few minutes. And the probability density function is the continuous equivalent of the probability mass function when we are talking about continuous random variables. But right now, we are just talking about discrete random variables. So in the discrete random variable, what we have associated with that random variable is something called a probability mass function, PMF. And the probability mass function does the following. What it does is that it takes every element in the support of x and maps it to a number between 0 and 1. Right? So this function is defining the probability of each of those possible events that could happen, a heads or a tails, or in the case of the multiple coin tossing setting where you keep tossing until you get a heads, the number of times that you have to toss to get a heads, you're defining the probability of each of those events happening. Okay? Of course, the idea of events and all the probability theory that I'm eliding here is all discussed in a little bit more detail in the textbooks, so you should definitely go and look at more details over there. But this is all we need to think about for the moment. So what we are doing formally is that the function, this probability mass function, which I'm calling P of X here, P of capital X here, will take as input any element of the support of X, and it will return the probability of that particular event happening. Okay? So let's talk about a specific example. Right? Suppose I'm talking about that very simple case of tossing a coin just once. Okay? If I do that, then the support of X contains the number 0 and 1, and I can now define probabilities for each of these 2 possible events. Right? So let's say, just for argument's sake, that we have a fair coin, and if we have a fair coin, it's reasonable to assume that the probability of a tails is 0.5 and that of a heads is 0.52. So that's how I've written it out formally over here. Okay? So that's my probability mass function for this very simple case here. Okay? Now, the probability mass function, the PMF, allows us to also derive a related function called the cumulative distribution function. What the cumulative distribution function, or CDF, does is that it tells you the probability of observing a particular element in the support of X or something less than that. And formally we will write it like this. Capital F represents the CDF of a particular random variable. It can be any random variable. The capital F will always refer to the CDF of that random variable. So what we are saying here with this equation here is that when I write capital F X equal to 1, what I'm asking is, what is the probability of observing 1 or something less than that in this random variable X? Okay? And this probability is defined as the cumulative probability of observing all numbers starting with 1 and going downwards from 1. So in our particular case of tossing a coin only once, there are only 2 numbers in the support of X, and so I'm going to be looking at the probability of observing 1 or 0. Right? So I'm going to sum up those 2 probabilities, and that gives me the cumulative probability of observing 1 or something less than 1. Right? Similarly, I could ask, what's the probability of observing something like 0 or something less than 0? Well, there's nothing less than 0, right? So there I would just compute the probability of observing 0, and that's 0.5, right? So this is, in the simplest case, how the cumulative distribution function works. So now let's think about a more interesting situation where we are going to do 10 individual experiments over and over again. Each of the experiments has only one trial. Okay, so 10 experiments, each one with one trial, and what I'm going to do is just toss a coin once, that's one experiment. Then I toss the coin again, that's the second experiment, right? So that's what I'm doing here. I can simulate that situation on the computer using this function called RBARN, and I will talk more about these functions in a moment. This comes from the extra dist package. I'm using the RBARN function to do 10 experiments, and the probability of success, I'm assuming here, success is the probability of getting a heads, is 0.5. Just an arbitrary decision that I made. Okay? So what I'm getting as a result of running this command in R is this random sequence of zeros and ones. So ones represents success and zeros represents failure. So this is the kind of situation that the probability mass function is designed to address, right? So the probability mass function for this particular random variable, the Bernoulli random variable, where you have a single trial and a binary outcome, 0 or 1, is defined as shown here. So theta is the probability of success, 1 minus theta is the probability of failure, x is whether you have a 1 or a 0. Right? So if you plug in a probability into the theta and you plug in a 1 or a 0 into this equation, you get the probability of getting x, where x can be 1 or 0. Right? So that's the basic setup here for this very simple case. Now, you can use a function called the dBARN function, right, to compute this probability that I've shown here, right? So this probability mass function is built into R in this library, and you can actually use this function to compute the values from this probability mass function, right? So here what I'm doing is I'm asking, what's the probability of observing 0 when the probability of success is 0.5? So I'm literally plugging in 0.5 into the thetas here and 0 into the x's here. And as a result, I'm going to get the answer back 0.5, which is, I mean, really trivial, but it's good to understand what's happening here with this dBARN function. It's really implementing this probability mass function here. Okay. All right. So I can similarly ask the same question about x equal to 1, right? What's the probability of observing 1? That will of course be 0.5 because I already specified that. So this kind of a silly demonstration because I specified the probability of success here. And if you look at the probability mass function, it's pretty obvious if you plug in a 0.5 into the theta that you're going to get a 0.5 here, right? So you might want to play around with theta here and check what happens with theta equal to 0.1. The probability of success is 0.1, right? What would be the probability of getting a 0 and a 1? You can try that out, or try it out with theta equal to 0.9 or something, right? So that will help you see where, what this function is doing and what information it's giving you. Also notice that because 0 and 1 are the entirety of the support of x, in this particular example, the total probability of getting one of the possible elements in the support of x is going to be 1. That's guaranteed. The probability of any one of the possible events happening is, of course, going to be 1. Right? All right, so now, how do I compute the cumulative distribution function in R, right? So this, of course, we can do on paper in this simple example. We can do it by hand. We don't need a computer for this. But for the more general case, there is a built-in function in R that does this computation for you, calculating the cumulative distribution function for you. And that is the P family of functions. In the case of the Bernoulli, it's the P-Bayesian function. So here what I'm asking is, what's the probability of getting 1 or something less than 1? So what is something less than 1? It's 0, right? So it's going to compute the cumulative probability of getting 1 or 0, and that, of course, will have to be 1. Similarly, I can ask, what's the probability of observing 0 or something less than that? There's nothing less than 0. Therefore, what I'm going to get back is exactly the same number as in the probability mass function that we computed earlier with dBAM, right? Because that's exactly what we would be computing here. So that's basically the important thing to understand here in the discrete random variable case is that there's a probability mass function associated with a discrete random variable, and we can derive from the probability mass function the cumulative distribution function. So the CDF and the PMF, they are basically two sides of the same coin. They are answering different questions, but the CDF is derived from the PDF, right? Okay, so let's look at another example of a discrete random variable, and this one is a random variable that we'll be using all the time when we are doing data analysis with binary outcomes. This is the binomial random variable. The binomial random variable, what we are assuming is that we have more than one trial when we toss the coin, right? So in the coin tossing experiment, I did an experiment where I tossed the coin only once, and that counts as one experiment. But I could have done the experiment, defined the experiment to be the following. I could assume that I'm going to count one experiment as being 10 coin tosses. So I toss the coin 10 times, and I count the number of heads I get in those 10 coin tosses. So that's the situation I'm talking about here. So this is different from the Bernoulli case, where the probability mass function was this one here, and you had only 0 and 1 as the possible elements in the support of x. In the binomial PMF, the situation is different, because I have, in the example I'm talking about right now, suppose I toss the coin 10 times, and that counts as one experiment, then I can get 11 possible events. 0 heads in 10 coin tosses, 1 heads, 2, 3, 4, and all the way up to 10. So 11 possible outcomes can happen. And also, if I get 1 heads, there are 10 different ways that I can get 1 heads, right? I could get a heads followed by 9 tails, tails, 1 heads, and followed by 8 tails, and so on, right? So that's why the Bernoulli probability mass function changes in the binomial. It has this extra term here, which takes into account that you could get 1 heads in more than one way, right? So the probability mass function for the binomial is exactly the same as the Bernoulli, but the only difference is that we've got more than one trial, and for that reason we have to take into account the fact that we could have more than one way in which we get a particular event, like 1 heads, right? So this time, in this particular case, if we have n trials, right, and n in my example was 10, the number of elements in the support of x would be n plus 1, right? So 10 plus 1, because you could also have 0 heads in one particular case, as one particular possible outcome. Okay, so So this is just the function n choose k that I showed you earlier. This function here in R is available as the choose function. So you can look at the number of permutations that you would get, the number of possible ways in which you can get two heads when you toss a coin 10 times, right? So now I want to just quickly visualize some of the, shapes that you're going to get in the probability mass function for the binomial in the case that you toss the coin 10 times. So if you toss the coin 10 times, 11 possible outcomes. What is the shape of the probability mass function graphically, okay? So in this particular example that I'm showing you here, I'm assuming that theta is 0.5. So the probability of success is 0.5. And in that particular case, if you look at the x-axis, you'll see the numbers going from 0 to 10. And what you'll find is that the most likely value, the highest probability value here is 5. Okay? If I change the probability of success to, 0.1, right? Then the most likely value in the support of x is going to be 1. Right? The shape of the probability mass function shifts to the left because I changed the probability of success to be 0.1. If I change the probability of success to be 0.9, then the shape of the PMF will change and shift to the right, right? And the most likely value will be 9 out of 10. So this visualizes, the probability mass function for us in the case of the binomial. And this function will play a very important role for us when we are doing statistical inference later on. So just to summarize, the most important thing I wanted to get across in this part of the lecture is the 4 critical R functions that we have encountered in the case of the binomial random variable. Actually, we encountered only 3, right? So I showed you the R binom function, also the R band function, but I'll talk about the binomial now. R binom function generates random data. The D binom function tells me the probability of each possible outcome, and the P binom function gives us the cumulative distribution function, right? So you can plug in any of the possible events, the elements in the support of X, and you get back the cumulative probability of observing that particular event or something, or some number corresponding to an event that corresponds to a number less than that particular one. All right, so let's make this concrete. Let's summarize the functions that I want you to understand. The R binom function, right? This function generates random data. I showed you how this works. When you have one trial and you're doing 10 individual experiments in the binomial distribution with a probability of success 0.5, you'll get a random sequence of zeros and ones, right? Now, if I were going to do 10 separate experiments, each with sample size 10, I would not get zeros and ones this time. What I would get is the number of successes I had in each of the 10 experiments. So that's why I'm getting, 5, 5, 7, 6, 4, etc. in the outcomes here. Right? So there's 2 different ways in which you can use this R binom function. Okay. So the second function that we've already seen is the D binom function, right, which tells us the probability of each of the possible outcomes. So what I did here is I shortcutted the process by just entering a vector of value, 11 numbers here, and what it prints out for me is the probability of each one of those 11 possible events, right? That's what the P binom function does, the probability mass function. Then I can compute the cumulative distribution function by using the P binom function, right? So what this function is doing is that it's calculating the cumulative probabilities, and you can see the probability of observing 10 or something less than that is guaranteed to be 1, obviously, right? Because that encompasses the entire range of possible events that can happen. Now, the one function I did not introduce yet, I'm now introducing it for the first time, which is the 4th critical function in this family of functions, is the Q binom function. The Q binom function is the inverse of the P binom function. So if you recall, in the P binom function, what I'm doing is I'm taking as input one of the possible elements in the support of X and returning the probability of the event corresponding to that element in the support of X, right? the inverse of the CDF will literally do the opposite. So if I will give the inverse of the CDF a probability, and it will return the quantile that that probability corresponds to, right? So so what I mean is that in this probability mass function, I'm getting the probability of each of these individual events, 0, 1, 2, 3, 4, 5. I can use this table to compute the cumulative distribution function. How would I do that? If I want to know the probability of observing 10 or something less than that, I'm going to sum up all these 11 numbers. If I want to know the probability of observing sorry, where am I now? Yes, 9 or something less than that, then I would sum up all these 10 numbers, right? 8 or less than that, I would be summing up all these numbers here from 8 down to 0, right? That would give me the cumulative distribution function. That's this one here. That's what I'm doing in this plot here. I'm literally summing up those probabilities, right, to get the cumulative distribution function. The inverse of this function is what the Q binom function gives us, right? So in the Q binom function, what I'm doing is I'm giving as input into the Q binom function a probability, and that what this function will return to me is the quantile that corresponds to that cumulative probability from the CDF. Okay, so what I've done here is first I computed the CDF of the binomial distribution for this particular binomial distribution with theta equal to 0.5, and I saved the cumulative probabilities, which I drew graphically here, right? I saved them in a vector called probs, and what I'm doing is I'm just plugging in this vector of probabilities, which are the cumulative distribution functions, output into the Q binom function, because the Q binom function is the inverse of the CDF. It's going to return for me the elements in the support of X that correspond to those cumulative probabilities. So that's why I end up with 0 to 10 here. Okay, so that's what's coming out here. Here it's somewhat confusing because this is actually 10 continued over to this line. This is just a formatting problem. Maybe if I made this a little bit wider, if I made this, I can't see the end of this figure, this thing here, right? Yeah, here, right? So if I made this a little bit wider, you'd see that this is 10 here, okay? So these are the elements in the support of X that correspond to those cumulative probabilities. So the cumulative distribution function is this figure here, right? So it's taking as input a probability and returning a quantile. So it's the inverse of the CDF. So what we've learned is that we've looked at 4 important functions that are associated with the binomial distribution: the R binom function, the D binom function, the P binom function, and the Q binom function. I call these the DPQR family of functions. They're available for every distribution that is provided in R, and so you can use this DPQR family to study the properties of any function that you're interested in using for your statistical modeling. And this is what we will be doing in the coming lectures. We'll be using the DPQR family of functions to study distributions and what information they represent for us. Okay. All right, so that's the end of this part of the lecture regarding discrete random variables. In the next part, I'm going to talk about continuous random variables. The next important topic for us is the idea of the likelihood function. So let's first take a look at the binomial distribution, the binomial random variable, and see how the likelihood function emerges from the probability mass function there. So in the binomial random variable, right, we had this probability mass function, which I have now instantiated with a particular set of outcomes from an experiment. So let's say I do an experiment with 10 trials, and I get 7 heads or 7 successes in 10 trials. So the probability mass function can give me the probability of obtaining 7 heads in 10 trials using the D binom function, right? I could do that. I could also use the P binom function by computing the cumulative probability of observing 7 or less heads, and then subtracting from that the cumulative probability of observing 6 or less heads, right? So there's 2 ways to do that. But the main point is that the probability mass function allows me to calculate the probability of particular events, such as 7 successes out of 10. Now, whenever we compute that probability, we have to specify some value for theta, the probability of success. Otherwise, we can't compute the probability of getting any of the numbers from 0 to 10 here in this particular scenario. Now, you could take the probability mass function and fix the data. So these are the actual results of an experiment. I've got 10 trials, I've got 7 successes. Those are now fixed. Those are fixed constants. Once you've done the experiments, those numbers are not going to change, right? So you could take the probability mass function and treat it as a function of theta. So now you could think of the same function, the probability mass function, as a completely different function that is not a function of different values for k. N is of course fixed when you start the experiment, right? But k is the possible elements in the support of x, which represents the different events that can happen. But you can take the probability mass function, fix the data once you've collected the data, and treat the probability mass function as a function of the parameter or parameters in that function. And in that situation, that function is now called a likelihood function and represents the different likelihoods of the parameter or parameters given the data that you have. So I've written it out here. This curly L here represents the likelihood function, and I'm now computing a function that tells me the different likelihoods of different values of theta, assuming that I had 7 successes in 10 trials. Okay? So you can actually plot this function now. Remember that theta in this case is a value, continuous value ranging from 0 to 1 because it represents a probability. So I can now plot this function by plugging in different values for the probability. So on the x-axis, I'm just putting in different values for theta and computing the function and connecting the lines, and I get a curve that looks like this. This curve is the likelihood function. For different values of theta, it's telling you what the more or less likely values are. And what you can see here is that in the case where I have 7 successes out of 10 trials, the most likely value of theta is 0.7. Okay? So what we say in statistics is that 0.7 is the maximum likelihood estimate of the parameter theta. Right? And the reason it's the maximum likelihood estimate is because of the shape of this curve and the maximum point, which is at 0.7 here, when we have 7 successes out of 10. If we had had 4 successes out of 10, then the maximum likelihood estimate of theta would be 0.4. Okay? All right, so one important thing to remember about the maximum likelihood estimate is that it will fluctuate under repeated sampling. The maximum likelihood estimate will fluctuate from one number to the other. So if the true value of theta is, let's say, whatever this is, I've forgotten what I wrote here, but whatever the true value is this horizontal line, right? I can't actually see that number. That's why I'm not able to tell you what exactly that number is. But this horizontal line represents the true value of the parameter, and the x-axis represents different sample sizes, increasing sample sizes, okay? And so what I'm doing here is I'm simulating an experiment done repeatedly. And what you'll notice is that for smaller sample sizes, the maximum likelihood estimate, that means the number of successes out of n trials, k successes out of n trials, can fluctuate wildly, but each of those estimates is a maximum likelihood estimate. It's the most likely value of theta given the data that you have. It doesn't mean that each of these maximum likelihood estimates represents the true value. That's obviously not true. If you look at this gold standard value that I have here, the values are fluctuating around the true value of theta. But each one of these dots represents a maximum likelihood estimate for the given data that we happen to get generated from the random process. And what you should notice is that as I increase sample size, the maximum likelihood estimate starts to converge on the true value of the parameter. That's the real meaning of the maximum likelihood estimate, that as the sample size goes to infinity, I'm going to approach the true value of the parameter if I use the maximum likelihood estimate from the data. The maximum likelihood estimate does not mean, and this is a very common misunderstanding, does not mean that anytime you do an experiment, regardless of sample size, if you do an experiment and you calculate the maximum likelihood estimate, that maximum likelihood estimate is not necessarily telling you the true value of the parameter. It's still a maximum likelihood estimate, but it's not necessarily telling you the true value of the parameter. So for example, here, this dot here is a huge overestimate of the parameter. This dot here, can I find my cursor? Yeah, this dot here is a huge underestimate of the parameter, but both those numbers are maximum likelihood estimates. Okay, so the MLE need not represent the true value of the parameter, but it is the maximum likelihood estimate in this sense. In the sense of this curve that I'm showing you here, here's the maximum point, 0.7 for this particular case. All right, so that was the discrete case. Now think about the likelihood function in the normal case. And in this case, just to simplify the discussion so as to not have too many parameters in play, I'm going to set sigma to 1. We fix sigma to be a known value of 1. And we think about the likelihood function for mu given the data, right? So of course I've put sigma here as a variable. So technically this is going to be a joint bivariate distribution. I will get to that topic in a moment. But right now I'm only thinking about this likelihood function as a function of mu. But more generally, in the normal distribution, we would talk about the likelihood function as a function of 2 parameters because there are 2 parameters in the model. Okay? But we are talking about the likelihood function of mu here, assuming that sigma is fixed at 1 and x is the data that we have observed, right? So let's do a very simple demonstration of the likelihood function now and assume that we have just a single data point, just one data point, x is equal to 0. We've observed that in an experiment. And now I'm going to compute the likelihood under different values of mu. So here we go. First, I've got mu x equal to 0. That's my observed data. Sigma is assumed to be 1. Let's compute the likelihood of mu being 0. So when I run this function dnorm, this dnorm function, remember earlier, was telling us the density of a particular data point, assuming some parameter values. That same probability density function is now being used as a likelihood function by fixing the data and assuming the function to be a function of mu in this case, right? So what I'm doing is I've plugged in this variable value mu equal to 0, and I'm calculating the likelihood of that value given the data that I have, okay? And that likelihood is 0.39, right? Now, what would be the likelihood for some other value of mu, right? So I'm just plugging and playing with different values of mu in this likelihood function now. So I've just taken another example of mu equal to 10. And what you should notice now is that the likelihood of mu equal to 10 is much, much smaller than the likelihood of mu being equal to 0, right? So this is a low likelihood situation. This is a high likelihood situation, right? So what this tells me practically is that given the data point x equal to 0, the most likely value that produce that data point, or the more likely value that produce the data point, is likely to be 0 and is less likely to be 10, right? So the likelihood function allows me to make a judgment about what the more or less likely values of the parameter or parameters would be given some data that I have. Right, so the likelihood function in this particular case looks like this, and as you can see, the maximum likelihood estimate in the case where the data point that we have is x equal to 0 is 0. So mu equal to 0 is the most likely value in this likelihood function, right? So now let's increase the complexity of the problem slightly. Okay, so instead of having one data point, x equal to 0, I'm going to have two data points that are assumed to be independent of each other. Okay, so let's assume that I've observed two data points, x1 and x2. x1 is 0, x2 is 1.5. And now what I can ask, the question I can ask with the denorm function is, what is the joint likelihood of particular values of mu? Remember, sigma is fixed at 1. For particular values of mu given the data that I have. Now, the way I would compute the joint likelihood given two independent data points is by simply multiplying the likelihoods of each of those two data points. We know how to do that for individual data points, x1 and x2. So here's the likelihood for mu equal to 0. Here's the likelihood for mu equal to 0 for the two data points here. So I multiply those two denorm values, and that gives me the joint likelihood of mu equal to 0 given the data that I have observed, right? Now, doing this multiplication can be difficult and problematic because of the decimal points that we are multiplying with each other, right? These numbers are going to be very small sometimes. So it actually makes more sense to work on the log scale where this multiplication becomes an addition, right? So what I'm doing here is I'm not computing the joint likelihood, but I'm computing the joint log likelihood, right? And because if you turn to the log scale, if you log transform a variable, if two numbers are being multiplied, if you take the log of those, then they become an addition, right? That's just a standard fact that you must know from high school. So now I've got the log likelihood for mu equal to 0 given data point x1, the log likelihood of mu equal to 0 given data point x2, and I'm doing that, computing that log likelihood by typing log equal to true, but I could have just taken denorm, you know, this statement here, this statement here, and wrapped around it the log function. It would be the same thing, okay? So I've just specified log equal to true, and that allows me to add those two log likelihoods. That's the same operation, but on the log scale. This multiplication is now an addition because we are on the log scale now. And so now I have the joint log likelihood of mu equal to 0 given the data that we have observed, right? So we could do all of this more compactly by creating a vector x that contains the two data points. So x is now a vector containing the two data points 0 and 1.5, and I've given to denorm as input the vector x, and now I'm computing the likelihood of 0 for each of the elements of x, summing them up because I'm working on the log scale, and I get exactly the same number as you see here. So this is a very general procedure now. If I have n data points that are independent, I can compute the joint log likelihood for different values of mu given some fixed value of sigma here, okay? So one interesting practical consequence of this is that one can use the log likelihoods of different values of mu to compare competing models fit. So you can basically use this as a model comparison method, right? So the question that I could ask now, given the data x equal to 0 and x1 equal to 0 and x2 equal to 1.5, I could ask the question, what's the most likely generative process that produced these data? Assuming a normal distribution with standard deviation 1, what's the most likely value of mu that produced these data? So the way I would answer that question is by plugging in repeatedly different values of mu, right? And checking which one gives me the highest number, right? So I can use the log likelihood calculations for different values of mu to decide which would be the most likely generative process that produced the data. In other words, what would be the most likely value of mu that produced the data. And so what you'll see in this particular case is I'm just taking two numbers here, mu equal to 0 and mu equal to 10. And what you see is that the joint likelihood, log likelihood of mu equal to 0 is minus 2.9, but the joint log likelihood of mu equal to 10 is much smaller. It's minus 87. Okay, so if I had to decide between mu equal to 0 and mu equal to 10 as the underlying mean that might have produced the observed data, I would prefer mu equal to 0. Why? Because the likelihood is higher, okay, compared to 10. So this model comparison that I'm doing here is very similar to the analysis of variance that people do. The analysis of variance is a likelihood ratio test. It's really comparing log likelihoods of competing models. And so we will encounter this idea over and over again, also in the Bayesian setting when we talk about Bayes factors. In Bayes factors, we'll be doing something similar to this very simple demonstration of how you can choose between two models by having a baseline model. Here's my baseline model, comparing it with an alternative model, right? And deciding in favor of the alternative model here. All right. So more generally, you can write this in a much more compact way. I gave you a demonstration with one data point first, then with two data points, but you can generalize this now in a very compact notation where you can talk about the joint likelihood of mu and sigma. I don't need to assume that sigma is constant in the general case. So there are two parameters here that we're talking about. So what we are doing here to compute this likelihood, if you have n data points, so notice that x sub I represents each of the n data points which are independent, assumed independent. So these n independent data points, I'm going to compute the likelihood of each of these data points and multiply the likelihoods to get the joint likelihood of mu and sigma given the vector of data that I have observed, right? So this is on the original scale. Yeah, if I took the log of the likelihood, of the likelihood, I would end up with the log likelihood, which is traditionally written with this lowercase curly l. Yeah. So here I'm computing the log likelihoods instead of a product. This is the product term here. I'm using a summation because I'm summing up the log likelihoods, exactly what I did earlier, right? If you look here, I'm summing up the log likelihoods here. That's the most general statement that we, can write down for computing log likelihoods given some independent data. All right, so that's the important, idea that I wanted to get across regarding likelihoods and log likelihoods. We are going to be needing these ideas in the next chapter and beyond. The last thing I want to talk about in this part of the lecture is the expectation and variance of a random variable. I'm not going to discuss this in any detail. All I want to remind you of is something that you almost certainly know when I want to compute the maximum likelihood estimate. So suppose I'm assuming that the data are coming from a normal distribution with some mean mu and sigma, standard deviation sigma, right? In this scenario, right, if I have some data independent and identically distributed data, let's say I have n data points, x1 through xn, right? So I have n data points, they're independent, assumed to be independent. I could compute the maximum likelihood estimate of mu and of sigma, right, by calculating the sample mean, right? If I take the sample mean, it would be the sum of the x's, right, divided by the sample size. That gives me the sample mean, and I could compute an estimate of sigma, right, by taking the sum of the squared deviations, right, divided by n minus 1. Right? All these details, where do these equations come from? right? So this is not sigma, I'm sorry, I'm wrong about this. So this is sigma squared, right? So this would be an estimate of S squared would be an estimate of sigma squared. X bar would be an estimate of mu, right? So these are maximum likelihood estimates of these two parameters, mu and sigma squared. Okay, so where do these equations come from? They were not given to us by somebody who just stipulated it. These equations are derivable, and you can find the derivations. Of course, you'll find them in textbooks, obviously, but I derive them in these lecture notes, which I will make a recording for someday. But these lecture notes spell out the derivations if you're interested in seeing where these estimates analytically come from. Okay? It requires a little bit of calculus, but it's not very complicated. So regarding expectation and variance of random variables, we are going to be using these formulas that I just showed you for the mean and the variance when we are looking at analytical examples later on. So I just wanted to remind you of these standard formulas. I'm pretty sure that pretty much everyone has seen these at some point in their lives. So I don't need to dwell on it too much, but I do discuss it in detail in these lectures. So the second topic in chapter 1 has to do with continuous random variables. Now we're going to look at a version of random variable that is not as simple as the situation with coin tosses. That's the example we looked at with discrete random variables. So when we were talking about coin tosses, we had heads and tails. Think about the simplest possible case where you have just one coin toss, heads or tails. That's the Bernoulli random variable, right? So in this situation, what we have is a discrete outcome, right? We can either get a heads or a tails. You can't get 1.5 heads or half a heads or half a tails. But when you're recording data from, for example, an eye tracking experiment, you're going to have reading times that are, theoretically at least, they're continuous values, right? So 0 milliseconds would be the lower bound, but in principle, reading times could be any number, any continuous value larger than 0, equal to or larger than 0. So these kinds of variables are different from the discrete variables that we've been looking at with the discrete random variable. These are continuous variables, and for these continuous variables, we're going to assume that there is a mathematical object called a random variable, a continuous random variable, that's assumed to be generating that data, for example, reading times. Okay? And so instead of having a probability mass function, as in the discrete random variable, we are going to have in the continuous random variable probability density function, or PDF, and I'm going to designate that with this function name f, and the dot in the center here just represents the parameters that will go into this function. So from this point onwards in the lectures and in the textbook, we'll be referring to random variables as being associated with a particular probability mass function or a probability density function. And so when you see a statement like this is capital X representing the name of the random variable. Tilde, this tilde here, represents the assumption that we are assuming that the random variable has associated with it a particular probability mass function, or as in this continuous case, a probability density function. And the important assumption here is that we are assuming that the data are coming from this particular PMF or PDF. Okay, so that's what this statement represents, that the data are assumed to be coming from some particular probability density function. So let's take a concrete example. So we often encounter the normal distribution in statistics, where we are assuming that the data are coming from a normal distribution which is parameterized by two variables, the mu and sigma. Mu is the location parameter, or the mean here, and sigma is the scale parameter, or the standard deviation. The underlying probability density function associated with the normal is this statement here, this equation here. And so what I'm showing you here is that particular data points, which are now represented with lowercase x. Capital X represents the abstract object, the random variable. Lowercase x represents either a single data point that is being generated, for example, with the R family of functions that we saw in the binomial case, some data that has been generated, some specific data that has been produced by that generative process, conditional on the assumption, that's what that vertical bar is, that the parameters of the PDF are mu and sigma. So that's what the left-hand side means, that the PDF is a PDF or probability density function that represents the densities of different data points. This could be one data point, X could be one data point, or a vector of data points, right? Assuming a particular set of parameters, mu and sigma, in this particular example of the normal distribution. And the right-hand side gives you the shape, the mathematical form of the normal distribution that determines that familiar shape of the normal distribution. Now remember that in this normal distribution, the support of x ranges from -infinity to +infinity. So all real numbers between those two ranges. Okay, that's the default assumption in the normal distribution. We can of course truncate the normal distribution such that it's bounded at a lower bound, for example 0, or bounded at an upper bound, or both, right? So you could truncate a normal distribution. We will do this later on. But right now, let's just take the standard case where we've got a normal distribution parameterized by these two variables, these two parameters, mu and sigma, okay? So that's an example of a continuous random variable and the PDF associated with this random variable. All right, so I think I already explained all these details, so I don't need to unpack them here. Now, one important detail to remember and to understand about the continuous random variable in contrast to the discrete random variable is the following. In the discrete random variable case, we could calculate the probability of every possible event by running the D family of functions. So for example, in the D-ban distribution, what I'm getting from this discrete random variable, from the PDF of this the PMF of this discrete random variable is the probability of this event 1, right? Assuming a particular probability of success and so on. So for any particular event, I can get a probability out of the probability mass function in the discrete case. In the continuous case, the situation is different, right? So in the continuous case, I can't ask questions like, for the binomial and the Bernoulli distribution where I'm asking about the probabilities of point values like 1 or 2 and so on in these particular settings that I showed you earlier. In the continuous distribution, in the continuous case of the random variable, the probability of a particular event, that means an element in the support of x, will always be 0. That's because probability is defined as the area under the curve, right? So if you think about a continuous distribution, something like this here, right? So this is a normal my cartoon version of a normal distribution, and here are the possible elements, that could be generated. The support of x is represented by this real number line here, right? So the support of x, all the possible values on the x-axis, the total probability of these has to sum to 1, right? But these are continuous values. So the way we define probabilities in the continuous case is the area under the curve. So the assumption is that so you have to remember that this distribution is going from -infinity to +infinity. So obviously I can't draw the normal distribution going off into infinity, so I'm just truncating it here in this figure. But you have to remember that this the real number line is going off in both directions, right? So that the total probability of any possible event happening, right, is the area under the curve, and this area under the curve has to sum to 1, right? And so in the continuous random variable, whenever we talk about a point value in the support of x, right, the area under the curve is always going to be 0, right? Because you can approximate the area under the curve by, drawing a rectangle like this, and the area under the curve in this approximate region would be the length times the length times the width, right? If the width is 0, then the area under the curve is 0. Therefore, for any particular value, call it x1 or something, right, the area under the curve is going to be 0. Therefore, in the continuous case, the probability of that particular number x sub 1 being observed is always going to be 0 every single time. There's no way around that, right? It's because of the nature of the random variable that we're talking about here. It's a continuous value here. So unlike the discrete case, in the continuous random variable, the probability of any one particular outcome will always be 0, and therefore the only kind of question that we can really ask is what is the probability of observing something between, let's say, x1 and x2, right? What's the probability of observing some value between these two numbers here, right? So that would be this area under the curve. These are the kind of questions that we can ask. So what this amounts to asking is, what's the probability of observing something between so which one is the smaller one, x2 and x1, right? So that's the kind of question that we can ask and answer in the case of the continuous random variable. This kind of question always has the answer 0. Okay, that's an important difference between the discrete and the continuous random variable. So as I said, what we can get out of a probability density function in the continuous random variable is the probability of observing events between some numerical range like x1 and x2, as I've shown you here. But this kind of question we can answer in the case of continuous random variables, and the answer will always be the area under the curve being representing the probability of that range of events happening, right? So you can imagine now, how would I compute such a probability, right? In a continuous random variable, I would do this by using the cumulative distribution function that is related to the probability density function, right? So if f of x here is the normal random variable that I just showed you earlier, then I could compute the area under the curve between some value u and negative infinity to get the cumulative probability of observing that value or something less than that. That is completely straightforward, and that's exactly what we did with the cumulative distribution function in the case of the binomial and the Bernoulli random variable, right? So it's the same setup. We have got the probability density function now instead of the probability mass function, and we can derive a cumulative distribution function by carrying out this summation, this area under the curve. This integral sign is just the summation in continuous space, right? The sum symbol, right? In continuous space. So it's not something that is radically different from what we talked about in the discrete case. All right. So let's now meditate for a few minutes on the normal distribution and think about one specific case of the normal distribution, namely the standard normal distribution. This is the distribution where mu is equal to 0 and standard deviation sigma is 1, right? So this kind of this is called the standard normal distribution. This kind of distribution is very commonly used in Bayesian statistics, and we will encounter it over and over again. So it's good to understand some key properties of this distribution. First of all, it's a symmetric distribution, right? It's going to have the same shape on the left-hand side, left and right of the center point, which is mu. The other important property that is important to remember for the standard normal distribution is that if you go +1 and -1 standard deviations to the left and right of the standard normal, you will cover 68% of the area under the curve. So this is shown graphically here. This is my standard normal distribution. If I go +1, -1 to the left and right, I cover 68% of the area under the curve, right? Similarly, if I go +2 and -2 standard deviations to the right and left, I cover 95% of the area under the curve. I'm lying slightly here. It's actually 1.96, plus minus 1.96, but 1.96 is close enough to 2. So let's just say 2, right? So +-2 standard deviations around the mean covers 95% of the area under the curve. And finally, if we go +-3 times around the mean, we cover 99.7% of the area under the curve. This is important to understand because later on we will be summarizing distributions that we will obtain as a result of our statistical modeling. So this property is going to be very useful for us about normal distributions. This property will be useful to us when summarizing our results from statistical modeling. Now, more generally, for any normal distribution with mean, mu, and standard deviation sigma, we can go one standard deviation, 1 sigma plus minus mu will cover 68% of the area under the curve. 2 sigma plus minus 2 sigma around the mean, mu, will cover 95%. Of course, again, it's 1.96, not 2, but I'm just going to say +-2, and will cover 95% of the area under the curve, and +-3 standard deviations, whatever the standard deviation is, right, in the normal distribution, +-3 standard deviations will cover 99.7% of the area under the curve. This is an invariant property of the normal distribution, and it will be very useful to us later on when we are summarizing distributions that we are going to approximate with the normal, right? Now, another important thing to understand about distributions in general, but I'm currently just talking about the normal distribution, is that every probability density function and probability mass function has two components. One component is the kernel, which determines the shape of the distribution, and the other component is the normalizing constant. That normalizing constant ensures that the area under the curve in the probability density function sums up to 1. That's the function of the normalizing constant. The function of the kernel of the distribution is to determine the shape of the distribution. So in the case of the normal, if you look at the specification of the normal distribution, this part here, the exponential part, this determines the symmetrical shape of that distribution. But this left-hand side here, 1/2 square root of 2 pi sigma squared, this is the normalizing constant, which is a constant factor by which you will multiply the kernel to make the area under the curve sum up to 1. So I will explain this now. And in order to explain this, what I'm going to do is I'm going to pull out the kernel of the normal distribution and rewrite it as g of x. Okay, so this is just the kernel of the distribution. Now, what I can do is I can write this function out in R. Okay, so I've created a function for the standard normal distribution. I'm just writing out the kernel here, and I'm calling it g. And now if I integrate this function from -infinity to +infinity, can you see this? Yeah, the f has flipped over to the next line, but it is going from -infinity to +infinity, and I compute the area under the curve through that integral. That integrate function is computing the area under the curve. It's summing up all the area under this between those two bounds, minus and plus infinity. So what I get is an area of 2.5. That's not That's not correct, because that doesn't make it a proper probability density function, because the area under the curve by definition in a probability density function has to sum up to 1. So the kernel alone does not have an area under the curve that sums up to 1. But if I were to divide the kernel, by 2.5 or whatever that number is, I would get the area summing up to 1. Right? So that's just this is the constant by which I have to introduce into the function that represents the kernel g, right? To get the area to sum up to 1. Right? So we can see this graphically. So what I'm doing is I'm plotting the function g here, and you can see that the shape is exactly like a normal distribution, but the y-axis is rather different from the standard normal distribution, where I do have the normalizing constant present. So here I have the normalizing constant present. Look at the range of the y-axis here, and here I do not have the normalizing constant present, and you can see that the area under the curve is much larger because the y-axis has a larger value here. Okay, so in a proper probability density function, I need to make sure that the area under the curve sums to 1, and the normalizing constant does that job for me. This will become very important from chapter 2 onwards, when we start using Bayes' rule for doing data analysis. All right, so now just as an aside, I want to just point out that if I have a kernel of a distribution like g of x, which I just defined a few seconds ago, this kernel, if I want to know what the normalizing constant should be, basically the question I'm asking is, what is the constant k such that the area under the curve sums up to 1? So I need to solve for the constant k. That's my goal, right? And solving for the constant k is super easy here, because I just multiply both sides by this integral, or rather I divide both sides by this integral, and I end up with k being equal to 1 over the integral of g of x with respect to d of x, with respect to x. So just to illustrate how I would do this, right? So what I'm doing here is I'm calculating k, which is 1 over that integral. I'm literally doing this calculation here, and I save that value in the variable k, and so that's this number here, right? So this is 1 over the integral of g of x, right? And this normalizing constant is what will ensure that the area under the curve sums to 1. And in fact, because my sigma value is 1, what you should notice is that 1 over the square root of 2 pi 1 squared, right, is also the same number that I'm getting here when I do the integral. That's pretty cool, right? So what I'm really doing is this k is literally the normalizing constant that we encounter in the normal distribution. Okay. All right. So this is just the final point that I wanted to make here, that in g of x, right, in that function with just the kernel, if I multiply it with the normalizing constant, the area now does sum to 1. Area under the curve sums to 1. So this is important to understand, that a normal distribution or any probability density function or probability mass function has two parts, the kernel and the normalizing constant. And as I said, the practical implication of the normalizing constant will become clear when we turn to chapter 2. Okay, so just like the dpqr family of functions in the binomial distribution, in the discrete random variable, we have the dpqr family of functions in the normal distribution. In every distribution that's available in R, you will have the dpqr family available. Right, so here I'm generating some random data from a standard normal distribution, 5 data points, right? Because R assumes that the distribution is a standard normal by default, right? I could just not specify the mean and standard deviation to generate data from the standard normal distribution. So if I just write R norm and generate 5 data points from the normal distribution, it's going to assume, R is going to assume that I'm generating data from the standard normal. If I specify the mean and standard deviation to be something other than 0 and 1, then I will get data from that particular normal distribution, not the standard normal. So I'm just showing you here that the default, parameter values for the mean and sigma, mu and standard deviation sigma in the normal in R is 0 and 1 respectively. So that's just generating random data. You can see that I'm going to get different numbers each time I run this function. Okay. The second thing I can of course do is compute the cumulative distribution function, and that's available with the p-norm function. So this function is now answering the question, what's the probability of observing 2 or something less than 2 in the standard normal distribution? Notice that I didn't specify the mean and standard deviation, so the R therefore assumes that mu is 0 and sigma is 1. Okay, this is standard normal. So I could of course also ask the question, what's the probability of observing some number like 2 or something larger than 2? I would still use the cumulative distribution function for that. And the one way to do that would be to specify lower.tail equal to false when querying the p-norm function. So what this function is now doing is that this function is simply saying, so when I ask the question for the standard normal, if I ask what's the probability of observing a number like 2 or something less than 2, right? That the command for that is p norm 2, right? So that's giving me this area under the curve. But remember that the area under the curve has to sum up to 1. Therefore, once I know this quantity, I also know this quantity, right? It's 1 minus whatever p norm 2 is, right? That's one way to find out, to answer the question, what's the probability of observing a number like 2 or something larger than that, right? So these questions can be answered by these two questions, this question and this question can be answered by just using the p-norm function. But in addition, if you are asking questions about a value like 2 or something larger than that, what you can do is to specify lower tail equal to false. And what that function is doing is that it's specifying that you should calculate the area under the curve to the right of the number that's given, not to the left of the number that's given, right? So these are two ways in which you could calculate this quantity, the probability of observing x or something, observing 2 or something larger than 2. Yeah? So the next thing that we want to look at is the q-norm function. So this is the inverse of the CDF, just like in the binomial. We give as input into the q-norm function a probability, and q-norm returns to you the quantile that represents the value where, so this is difficult to say in words, right? So basically what this function is doing is, right, it's telling me the probability of observing some value like q or something less than that. So what I'm specifying is this probability, 0.97 in this example, and this is the input into the q-norm function, and what is returning for me is this quantile, right? So it's telling me what is the quantile q, right, such that 95% of the area under the curve is to the left of it, right? That's the purpose of this q-norm function. Also a very useful function. Okay, finally we also have a d function for the normal distribution. That's the d-norm function, and what this function is giving you is not the probability of observing a particular value. Remember that probability is 0. What this is giving you for a particular number, it's telling you the density of that number in the probability distribution density function, right? So the input to the d-norm function is a quantile value, so one of the x-axis values, and what's being returned is the result of that function, the output of that function, namely the point on the curve that corresponds to that particular point value on the x-axis. Okay, so that's called the density of that number. It's not the probability. So you have to be very clear about the difference between probability and density in this particular context. Okay. So to summarize, what we have learned so far about the normal distribution is this DPQR family of functions. Thinking about the standard normal distribution, you can generate random data. So those are just some random data points I produced. You can calculate the density of any point on the x-axis. So that's the density for one. You can calculate the quantile that corresponds to the probability 0.841 or any other probability, right? So, and finally, you can calculate the cumulative probability of some particular range of values, right? Or some particular value like 1. So here I would be asking, what's the probability of observing 1 or something less than 1? Here I'm asking, what's the probability of observing some number like -1 or something less than 1? And the difference between those two gives me the area that is shaded in this curve, right? So that's a very important application of the p-norm function to figure out the area under the curve between two intervals, right? Okay, so here's another distribution. I mean, here I've been using the standard normal, but you could just plug in any mean on any standard deviation. Of course, the standard deviation has to be positive, it can't be negative, right? But the mean, of course, can be negative, and you will get a distribution centered around the mean with a particular spread around that mean that's determined by the standard deviation, right? So here are just some examples. Just an example of a normal distribution with a mean of 500 and standard deviation 100. Just an example. Here's the CDF corresponding to that particular distribution, right? So I can look up on the x-axis some particular value from the support of x and figure out the cumulative probability by looking at the y-axis, right? And the inverse of that, for these probabilities, I can figure out the corresponding quantile. So that's the main topic in this section. I want you to understand how the DPQR family of functions works in the normal distribution, and the fact that the normal distribution, like every other PDF and PMF, has two components, the kernel and the normalizing constant. So in the last part of this lecture for chapter 1, I'm going to talk about bivariate and more generally multivariate distributions. I'm going to again start with the simplest case of the discrete bivariate distribution. The data I'm showing you here is from a PhD dissertation by a former student of ours, Anna Lorinovic. And in this data set, what Anna had is two variables that are being collected in the experiment from each subject. So after each sentence is seen by the subject, they return a Likert rating from going from 1 to 7, so discrete values. And they also return an accuracy response to either a comprehension question, I've forgotten the details, but either a comprehension question or a grammaticality judgment or something. So basically we have two variables that are being collected simultaneously in the experiment. And so this is a situation where you have what you would call a bivariate distribution. So you've got two variables, x and y, we can call them, and you can see the data graphically here. So this is the x variable here, the 0 and 1 responses, and the Likert ratings are the y variable here, right? Or am I messing up the letters? I can't actually see the x and the y. So like one of them is a Likert rating and the other is, one of them is a Likert rating and the other is 0-1 response, right? So that's a bivariate distribution. And what you're looking at in this figure is a three-dimensional plot. There are two axes, one for each of the random variables, and the third axis is representing the probability of each of those possible joint outcomes, right? So that's why it's a three-dimensional plot here, okay? So this kind of distribution, which I just showed you graphically, is going to be called the joint probability mass function, or the joint PMF of those two random variables x and y. And so notice here that the PMF is being described in terms of two random variables, and the specific values of x and y would come in here. Okay, so what we now have in this probability mass function, I just showed this to you graphically, but what does this function look like as a table, as a probability mass function for two variables? I'll just show you what that looks like. But what we will get is, let me just first show you the joint probability mass function. On the rows here, you've got y equal to 0 and y equal to 1. These are the two possible values of the y random variable, capital Y random variable, and the 7 different possible values of the capital X random variable are given here in the columns, right? So this table going from these two rows to these 7 columns, this part here, this refers to the joint probability mass function for those two random variables in the discrete random variable case. Now, in this kind of joint probability mass function, there are two very useful distributions that we can derive. The first useful distribution is the marginal distribution of the random variable x and the marginal distribution of the random variable y. And the way we would do that, the definition for the marginal distribution is that if we want the marginal distribution of the random variable x, we sum over all the values of y, right? So we look at the joint probability mass function, that's this 2 by 7 table here, 2 by 7 table. And for figuring out the marginal, marginal probability distribution of x, I will look at this column, for example, the very first element in x, and then sum up these two values. That gives me the marginal probability of x equal to 1, ignoring the y values. So over the y, by summing over the y values, we are basically figuring out the marginal distribution of x equal to 1. Well, not the marginal distribution of x equal to 1, but the marginal distribution of the random variable x by going through all these 7 values and summing over, each of these columns here, these two columns. So what we are looking at the bottom row here in the margins of this table is the marginal probability distribution of the random variable capital X. So these are the probabilities of each of those x values, ignoring the y values completely, right? So just summing over those. Similarly, you can compute the marginal distribution of y, which only contains two possible values, 0 and 1, the support of y, by summing over those 7 values to get this number here. And for y equal to 0, for y equal to 1, we sum over these 7 values to get the probability for y equal to 1 here. So that's the marginal distribution of y, and here's the marginal distribution of x, right? Now notice that these probabilities will sum to 1 and these probabilities will sum to 1. They may not exactly sum to 1. If I were to do this calculation, that could be due to rounding errors, but technically they should sum to 1, okay? If we compute it right up to like the appropriate decimal places. Fine, so that's one important consequence of having a joint distribution like this, that you can compute the marginal distribution of y and the marginal distribution of x, right? And so graphically, you can visualize this situation graphically by looking at this plot and thinking about the distribution of y as follows. So if you just look at this 3-dimensional plot from the perspective of y alone, right? If you were standing here, you would not see anything relating to the x values, right? So you would see the total values for y equal to 0 and y equal to 1 if you look at it from here, by summing up all those numbers. And similarly here, right? If you were looking at the x random variable by ignoring the y values, then you would be able to get the marginal distribution graphically by summing up the values from the y variables, right? So that's the marginal distribution that you can compute quite easily, right? So graphically it looks like this, right? So I'm summing up those numbers for the probability density, probability mass function for x and the probability mass function for y. So you can derive the marginal distribution from the joint, the marginal PMF from the joint PMF of the random variables. The other interesting thing that you can compute from the joint probability mass function is the conditional distribution of x given a particular value of y. So you fix the value of y to, let's say, 0 or 1, and then you figure out the distribution x having conditioned the value of y to a particular number. So that's the conditional distribution of x given y, and similarly you can compute the conditional distribution of y given x, right? And the way to do that is by using the conditional probability rule here, which says that the conditional probability of x given y is the joint probability of x and y divided by the marginal probability of y, which we already computed a few seconds ago, right? So similarly, probability of x given y, oh sorry, am I messing up these things? So x given y and y given x, right? So these conditional distributions can be worked out using this conditional probability rule. So let's do it, okay? Let's do one example. So let's fix y to 0. We are conditioning the distribution of x on the scenario that y is equal to 0, right? So when y is equal to 0, right? We're conditioning on the scenario where y is fixed at 0, and we want to know the distribution of x conditional on y equal to 0. And what we are going to do is we are going to just apply the formula, right? Y is equal to 0, and we want the distribution of x conditional on that y value. So how do we do that? Well, the definition of a conditional distribution is the joint distribution divided by the relevant marginal distribution. So here's how I'm going to do this. I'm going to have to reference this table, which contains the joint distribution in the 2×7 table here, and the marginal distribution of x is here, marginal distribution of y is here, okay? So just applying the formula, y is equal to 0, we fixed that as 0. We want to know the probability of observing 1 in x given that y is 0. You apply the formula. The formula is look up the joint probability mass function for x equal to 1, y equal to 0, and divide by the marginal probability of y equal to 0. That's it. Okay, so let's look it up. What's the joint probability of x equal to 1, x equal to 1, x equal to 1, and y equal to 0, y equal to 0 is 0.018. That's that number over here in the numerator. And then what's the marginal probability of y equal to 0? That's over here, 0.291. So that's the denominator there, right? So that gives me the probability of observing 1 in the x variable, given that the value in the y variable is 0, right? So that's the conditional probability of x equal to 1 given that y is equal to 0, and we can do this now for every possible value of y. So 1, 2, 3, 4, 5, 6, 7, and that will eventually give us a distribution, right? A univariate distribution for the x random variable given that y is 0. So as an exercise, I strongly suggest that you try to I would like you to try to do this by hand, right? So work through the formulas and see whether you can figure out the conditional distribution of x given y and for specific values of y, and the conditional distribution of y given x for particular values of x. All right. So that's the discrete random variable case for the bivariate distribution. Now I'm going to talk about the continuous case where you have two bivariate distributions. So the example I'm going to use throughout here, even though I didn't make this totally explicit, is that I'm thinking about two normal random variables, okay? Random variable x and y, both are normally distributed and both have mean 0, okay? So I'm assuming that these distributions have mean 0. They could have any mean, it doesn't have to be 0. I'm just using an example here. Now here the situation is that I have two random variables, each of which has a mean and a standard deviation, okay? But there's one more important detail that becomes relevant when you have more than one distribution jointly involved, and that's the correlation between the two random variables. So the way we express the two standard deviations and the correlation between the two random variables is by something called a variance covariance matrix, which is traditionally written with a big sigma here. So it's a bit confusing that the big sigma is also used as a summation symbol, and so you might see it in other settings as well. So you have to know from context what the big sigma is referring to here. Here it's referring to the variance covariance matrix. Okay. So the variance covariance matrix encodes or encapsulates the two variances of the two random variables in the bivariate case that I'm talking about, and the correlation between them. So how does it do that? Along the diagonals of this variance covariance matrix, we have the two variances. Here's the variance of the random variable x. Here's the variance of the random variable y, right? And on the off diagonals, we have something called the covariance. The covariance is defined right here as the product of the correlation between the two random variables and the two standard deviations of the two random variables. That's the definition of covariance. Okay? So in the off diagonals we have the covariance, and along the diagonals we have the variance, and this constitutes the variance covariance matrix. It's a square matrix, so that means if I square and symmetric, so if I were to change the rows to column and columns to rows, I would still get the same matrix. It's a special kind of matrix that we have here. And so this capital sigma, this big sigma matrix, is what goes into the definition of the bivariate normal distribution. So what I've written here is in mathematical form, what I've written is that we have a bivariate normal distribution. So x is normally distributed, y is normally distributed, and these two guys are jointly distributed. So that's why I have put 2 here as a subscript. So there are 2 dimensions in this matrix. Okay, so x and y, 2 dimensions. The means are represented through a column vector, and the variance is represented by the variance covariance matrix that I just introduced. Okay, so this, what you're looking at right now, is the joint PDF, the probability density function of this kind of a bivariate normal distribution. Of course, the 2 distributions don't have to be normal. They can be, some other form. But right now I'm just using this simple example to illustrate the idea of a joint PDF. And notice that we have actually encountered this briefly earlier in the earlier part of this chapter, where I was talking about the likelihood function, right, of mu and sigma given the data. Right? If mu and sigma are both variables, then there's a joint likelihood function there of those 2 random variables. So one could, of course, it's not a probability density function, the likelihood function, but that means the area under the curve and under the surface of this three-dimensional figure that would constitute the bivariate distribution need not sum to 1, but still it is bivariate in that sense. So this is something that we have encountered in a slightly different form earlier. Now, the interesting thing with this distribution now is that graphically, what this distribution looks like is no longer that univariate normal distribution form that we are familiar with. The distribution actually, I'll just go forward a little bit, looks like a cone, right? So it's a surface that we're talking about, and the area under this surface, right? So not the area, but the volume under this surface is going to have to sum to 1 now, right? Because it's representing a probability, and the total probability has to be 1, right? So the volume under this surface that we're seeing in this cone is going to sum to 1. So that's this formal statement here. So what I'm saying here is that we have a bivariate normal distribution. Okay, that's this fxy, and if you sum up the area under the surface, so you have to do 2 integrals, because you have to integrate over x and then integrate over y, right? So that's why there are 2 integrals here. So that's the summing up along 2 dimensions, and the total sum under the surface, the volume would have to be equal to 1. Okay, so it's just the same situation as in the univariate case, except that there are 2 dimensions here that we are talking about. The joint CDF, can be derived from the joint PDF as well, right? And the way you would do that is that if you want to let's see, let's do this here, right? So yeah, so if we want to figure out in this kind of cone-shaped, three-dimensional cone-shaped, you know, probability density function, the joint probability density function, we want to know the probability of observing a value like u from the random variable x and a value like v from the random variable y. What we would do is exactly what we did in the univariate case. We are going to sum up the area under the curve going from u to negative infinity and then v to negative infinity. And so this summing up gives us the area under the curve, namely the probability of observing u and v or something less than that in this bivariate distribution. Okay, so that's how the joint cumulative distribution function can be derived from the joint probability density function in exactly the same way that it was done with the univariate case that we saw earlier, except that we are working with two random variables now. So there are two integrals involved here, right? All right, so, and just as in the discrete case that I showed you earlier, you can also derive the marginal distribution by summing over the other variables. So the marginal distribution of x will sum over all the values of y, and the summation is this integral here. And similarly, the marginal distribution of y given x will be here, right? So basically the same story that we have for the discrete case translates into the continuous case. Marginal and conditional distributions can all be derived, although I didn't discuss conditional distributions here. You can look it up in standard textbooks. For example, the Cairns textbook, it's called IPSUR. You can download it from the internet. I will link to it on the course webpage. But it's also mentioned in the textbook. You can look up the details on conditional distributions in continuous joint, in bivariate distributions like these. But the ideas are the same. Instead of summations and looking at joint and marginal distributions like we did earlier, we are going to be doing exactly the same thing, but instead of summations, we'll be doing integrals. That's the only difference here. Yeah. So you can now try to visualize, the different kinds of distributions you could have in this joint probability density function for bivariate normal distributions. So what I'm showing you here is that cone that I mentioned earlier that represents the two random variables, the joint probability density function. Here's the cone in that three-dimensional plot. On the left-hand side, you see the contour plot, so the view from above. So you can see what the cone looks like. It's a symmetric cone. And this is the scenario where you have zero correlation between the two variables. So in the off diagonals of the variance covariance matrix, the correlation parameter rho, which I showed you earlier, let me go back. Right, so this correlation parameter rho, if this is zero, then you have no correlation between the two variables, and this off diagonal will have value 0 because anything multiplied with 0 will be 0. And so this is the situation I'm showing you here. And if you look at the contour plot from above, the figure from above, you'll see that it's completely symmetric and there's basically no relationship between the two plots. This is the cumulative distribution function, the joint cumulative distribution function of the x and y random variables where they're uncorrelated, right? So this is what I just talked about a few minutes ago when I was talking about those integrals. So instead of having a single CDF as in the univariate normal, we have a surface now that represents the cumulative distribution function. Now here's a situation where this contour plot will illustrate to you a situation where x and y are negatively correlated, right? So then the cone is no longer symmetrical, it gets squished in this direction, right? And you see that squishing here as well. When one variable is increasing, the other is decreasing. That's the negative correlation here. And here's the cumulative distribution function for that kind of scenario. And similarly, if you had a positive correlation between the two random variables, then the contour plot would show you the squishing towards the right. As x increases, y also increases. And in 3 dimensions, the joint PDF looks like this. Okay, and here's the cumulative distribution function as well. So the practical relevance of bivariate and more generally multivariate distributions for us will be that we can generate, we can represent multivariate data mathematically using this formalism here by talking about the relationship between the variables. This becomes very important when we're talking about linear mixed models, right? Because in linear mixed models, you will have random effects, varying intercepts by subject and varying slopes by subject. Those are two random variables that may or may not be correlated. So you could have a positive correlation between the intercepts, the varying intercepts and the varying slopes. So we'll be modeling that relationship using a bivariate normal distribution. So this will be a bread and butter activity for us. And because simulating data is a central activity in statistical modeling, we are also going to be needing to generate simulated bivariate or multivariate distributions. So I'm going to demonstrate how to generate simulated data from a bivariate distribution. So what I'm doing here is I'm defining a big sigma, which is the variance covariance matrix. And what I'm doing here is I'm putting 5 squared as the variance for one random variable and 10 squared as the variance for the second random variable. So I'm just going to generate data from a bivariate normal. And on the off diagonals, I've got, let's see what I have here, okay? I've got the standard deviation for the first random variable, this is the square root of 5 squared. The standard deviation of the second random variable, which is square root of 10 squared, and a correlation parameter of 0.6. So that's the covariance between the two random variables, right? That's the covariance definition that I showed you earlier. So what I've done here is I've created a 2 by 2 variance covariance matrix, which I'm now going to use to generate simulated data. Okay, so how do I do that? There's a package called mass, right, in R, which has this function MVR norm. So it's just the R norm function, but for the multivariate case. Okay, so what we are doing now is we're going to generate 100 data points. That means we're going to generate 2 columns because there are 2 random variables being generated simultaneously, and the number of rows in that column will be 100. Okay, but there'll be 100 by 2 matrix is what we will generate now. So this U matrix, this U object here, U, will be 100 by 2 matrix because it will contain 100 data points for the random variable X, 100 data points for the random variable Y. We are assuming that both the variables have mean 0. Okay. Both random variables have mean 0, and the variance covariance matrix of those 2 random variables is big sigma. Okay, so all I have to now do is run this function MVR norm from the mass library, and I'm showing you the first 3 rows of this data frame here. Of course, there's 100 rows here, and as you can see, there are 2 columns. So now what I've done is I've generated pairs of data from the random variable X and the random variable Y, which have a correlation of 0.6 because I stipulated that in my variance covariance matrix. Okay, so graphically, you know, the output of this function of the MVR norm function is a matrix which I can now graphically plot, right? So on the x-axis I have U, on the U1, so the first column, and on the y-axis I have U2, the second column. And because I stipulated that the correlation is plus 0.6, you see this positive trend here in this plot as well. If I had gone back and changed this, and I advise you to try this at home, change this to minus 0.6, okay, minus 0.6 in both the off diagonals, okay, not just in one, but in both off diagonals. It has to be symmetric, right? So what you will find is when you draw this plot yourself, you will find that the correlation goes in this direction, in the negative direction. As a third exercise, you can also try changing this 0.6 in the off diagonals to 0. Okay, so no correlation between the two. Then generate the data and look at the bivariate plot, and you will see a round blob of points signifying no correlation between the 2 random variables. In other words, you'll be seeing something very similar to this plot that I'm showing you here, right? So you'll be seeing, instead of circles, you will see dots that represent the absence of any correlation between the 2 random variables, right? So as I mentioned a few minutes ago, the practical implication of all this material about bivariate distributions is that we will be using bivariate and multivariate distributions to very good effect when we are looking at linear mixed models, because we'll be relying on these kinds of multivariate distributions to represent correlations or relationships between random variables that represent individual level differences for subjects and items and things like that in the linear mixed modeling framework. So this part of chapter 1 is going to become important when we start looking at chapter 5, the linear mixed model or the hierarchical modeling framework. Right? It'll be a central topic there, and we will need it over and over again. So once you reach chapter 5, it may be useful to go back and look at chapter 1 to refresh your memory about how bivariate and multivariate distributions in general are set up. So one last thing I want to say here in this part of the lecture is that I only talked about bivariate distributions, but we could have any numbers of distributions involved, right? So if we had, let me see if I can do this, if I have enough space for this. So let's say I have 3 random variables, x, y, and z, okay? So this is not a bivariate distribution anymore, it is 3 variables. And so we are looking at a normal distribution with 3 dimensions now. And let's assume, you know, that the 3 distributions have some mu values. So I'm just writing them out as variables because they could be anything, right? They all have some mean. And then what will happen here is that there will be a big sigma variance covariance matrix, right? So the question you have to ask yourself is, what are the dimensions of this variance covariance matrix? The dimensions will be 3 by 3 because there are 3 random variables now. So what this random variable looks like is the following. It will be a 3 by 3 variance covariance matrix, right? So on the diagonals, I will have the variances of the 3 random variables. That's the diagonal, right? Now, on the off diagonals, I'm going to have the covariances. So here in this box here, I'm going to have the correlation between x and y, okay, multiplied by the 2 standard deviations. In this box here, I'm going to have, in this cell, I'm going to have the correlation between x and z, and the 2 standard deviations, x, z, sigma x and sigma z. Here in this box, I'm going to have the correlation between y and z, right, with sigma, I think is this visible? Yeah, this should be okay. Sigma y, sigma z, right? And notice that whatever appears in this upper triangle here, the same material, the same variables will appear in this lower triangle here. So I'm not going to write those out, right? Because they'll be exactly the same. So the important thing to understand here, I guess you can't see me anymore, but I guess it's not important that you can't see me. But the important thing to understand here is, or let me stand here so you can at least see my face. So the important thing to understand here is that the idea of the bivariate distribution generalizes to any number of variables, right? So you could have 3 random variables, you could have 8 random variables, okay? Then you would have an 8 by 8 variance covariance matrix with all these variances and covariances written out over here. And later on, when we are fitting complex linear mixed models or hierarchical models, we will often encounter situations where the varying intercepts and slopes are actually, there are 7 or 8 of them, you know, for subjects, and 7 or 8 of them for items. So we'll be working with these multivariate distributions when fitting hierarchical models, when we start looking at them in chapter 5 and beyond. Okay, so that's the introduction to bivariate and multivariate distributions. And with this, we are ready to now talk about Bayesian modeling, which I will turn to in the next chapter. So in this lecture, the lecture relating to chapter 1, I covered several really important ideas that I want you to take away at the end of the lecture, and you should be able to do the following. You should be able to understand how the DPQR family of functions works for the bivariate case, that is the discrete example, and the normal distribution case, right? So the continuous example. So here we had the binomial distribution, right? And then we had the normal distribution here. And so you should know how to use the DPQR family of functions for these two classes of distributions. Because what will happen is that we will have some data that will either come from some discrete distribution, it could be binomial, it could be a binomial distribution, right? And theta, this parameterized by this sample size and the theta parameter, which represents the probability of success, or the data could be coming from a normal distribution, right? A continuous distribution, which is parameterized by two parameters mu and sigma, right? So you could have the situation that we're going to be modeling is that we will be getting data from some discrete or continuous distribution. I introduced two examples, but there are many, many other distributions that we could have chosen as appropriate generative processes for producing data. And in order to understand the properties of these distributions, you need to be familiar with the DPQR family of functions. For simulating data, we need the R family of R functions, the R binom and R norm functions. So we'll be simulating a lot of data in the future. So that's one important thing we need to be able to do. Another important topic that I discussed was the idea of likelihood, right? And as I explained, likelihood is nothing other than the probability mass function or the probability density function seen as a function of the parameter in question. So for the binomial case, in the binomial case, the likelihood function is a function of theta. In the normal case, the likelihood function will be a function of mu and sigma, and so on. Whatever the underlying parameters are in the assumed distribution that you're working with, right? The likelihood function will be a function of the parameters that are involved, right? That's the second important idea. The third important idea is the idea of the multivariate distribution, the bivariate multivariate distribution. So scenarios like this, where the data are possibly correlated, right? So they're jointly distributed. And so in this kind of scenario, we have a joint probability mass function in the discrete case and a joint probability density function in the continuous case. And so the main skill I want you to have relating to multivariate distributions is that you should be able to at least describe a joint bivariate or a joint multivariate normal distribution. That means you need to have the ability to unpack, for example, in this case, you should be able to tell me, let's write it like this, xy, right? You should be able to tell me what the contents of the variance covariance matrix are in this kind of situation. This is a super important skill that we will need in hierarchical modeling. So you have to be very clear about how multivariate distributions, in particular multivariate normal distributions, are set up, because they are kind of the backbone of the hierarchical modeling framework. All right, so once these topics are clear, if you can do all these things, use the DPQR family of functions, understand what a likelihood function is, and be able to unpack a bivariate or multivariate normal distribution, we are ready to start doing some modeling with some serious data.